There's not much in biochemistry that I would consider to be easy, but our carbohydrate chapter is maybe a little easier than some of the other chapters. One of the reasons for that is because everything we learn is a rule, and as long as you know how to apply the rules, you can't go wrong. This next page of our notes is all the carbohydrate rules. Some we've learned and some we're still yet to learn. I don't really want to go over these now. Maybe we could fill these in our normal get-together time. Let's put this aside and move on to our next major type of work. The next page of our notes, which we have to turn a little bit, is called cyclization. And this is where we make carbohydrates a little trickier, a little more complex. We've already learned the Fischer structure of a bunch of different sugars. They're all really important. Now we want to learn that sugars can cyclize into rings. This makes it a little trickier. It's a little more three-dimensional. But the fact is, we have to do this because most sugars that we're going to talk about later in the class are in the cyclic form. So let's get right to it. What we have on our screen here is D-glucose. It doesn't look quite the same, but it is a 6-carbon aldose, and we have laid it down on its side. This is 1, 2, 3, 4, 5, and 6. Normally we look at it vertically in the Fischer structure, but in order to cyclize a sugar, the first thing we're going to do is take it and rotate it down 90 degrees. So let's do that. Let's rotate the Fischer structure 90 degrees clockwise. At that point, we're done with the first of 3 steps to cyclize glucose in this case. The next step is to wrap the ends away from us. It's a little difficult to demonstrate this, but if we take this backbone here and we take the termini and we wrap them away from us like this, what we have is carbons 2 and 3 coming out at you here in the plane of the paper, perhaps, and everything else is going back around. Think of it as like we're looking edge on to a plane that's now going into the paper. Lastly, and this is the critical part to the cyclization process, it's a chemical step. We're going to take the alcohol on carbon number 5 of glucose. Let's make a note of that in the third step here. The alcohol of the highest number chiral carbon. Sorry, we need a little more room there. The alcohol of the highest numbered chiral carbon, that in this case is number 5, attacks the carbonyl carbon. Let's go ahead and get that written down. And now I want to show you how it works. The alcohol of the highest numbered chiral carbon, it's right there. That's the alcohol of carbon number 5. It's got a free pair of electrons and it can attack, with that arrow, the carbon of the carbonyl. Now, when we do an arrow of attack like that, we end up with a new bond, and that's shown right there. When we attack that carbon, now we have 5 pairs of electrons around it, which is not acceptable, and we're going to do something that is very common in chemistry, and that is to take that carbonyl and elevate a pair of electrons from the double bond up. In fact, what we're going to do, instead of having it be an O- out there, which is what normally would happen, it's going to find a proton. And when that happens, we end up having a new OH. What was a carbonyl carbon is now a carbon-oxygen alcohol bond. So we've really transformed this, and I want to have you look at it and see that there's also one other thing that we transformed. Did you notice something else changed? I can show you. It's right here. This pair of electrons is going to come and go down to that oxygen, and we break that OH bond, that alcohol of carbon number 5. We break that H off and we lose the proton. Notice we've lost a proton and we've gained a proton. So we are still at C6 H12O6. We maintain that 1-to-1 ratio of carbon, hydrogen, and oxygen. At this point, we have a different isomer of glucose. I want to tell you, though, it is D-glucose. All right, let's make a few notes about this. First of all, in the cyclic form, we call this the Hayworth structure. That's as opposed to the Fischer structure, which was the linear form. The second thing I want to note is we still have the same numbering of the 6 carbons. 1, 2, 3, 4, 5, and 6. Next, and most importantly, I want to have you see that we no longer have a carbonyl. That carbonyl has been converted into an alcohol, and we have a new bond between the oxygen and what was the carbonyl carbon. This part right here is called a hemiacetal. Hemiacetal. It's a hemiacetal linkage making this cyclic. Okay, the last thing I want to make sure you see before we move on from this is that because we used the alcohol of carbon number 5 to make this new ring, which is a 6-membered ring with an oxygen in it, because we use carbon number 5, carbon number 6 is actually outside of the ring along with its alcohol. This is called an exocyclic carbon. Exocyclic carbon, right there, number 6, and it's above the ring in this case. And we sometimes refer to this as a flagpole carbon because the carbon is sitting up there like a flagpole, and the OH is kind of flapping around like a flag. It could be going this way, or it could rotate and go this way. It doesn't really matter. It can rotate around and go in any direction there. Okay, we've made our life a lot more complex, and we're still going to make it even more so in a moment. Let's stop here for this video and just say that we formed a new form of glucose that we call the Hayworth form of D-glucose, and we'll pick it up in the next video.